Okay, so I've risen. I'm finally back after a few months. I'm gonna be honest, I got lazy and I ran out of ideas. But nonetheless, I'm here, and today we are going to go over partial derivatives. Now, partial derivatives is a form of dealing with multivariable calculus, which is found outside of calculus A, B, and BC. Rather, it's actually in Calculus 3, which is a college level course. So am I qualified to teach this? Anyways, as I said, we are dealing now with multivariable calculus. That is, there are functions and planes represented by two or more entirely independent variables. And although I said this isn't found in the AP curriculum, it may sound familiar to you as parametric functions. Although it's important to consider that these are separate, because in parametric functions, your plane or your functions are dependent on one shared variable. The two independent variables are often x and y. Of course, they can be anything, and the dependent variable is oftentimes t. But they can be manipulated in such a way that your independent variables are actually dependent of one another. This isn't the case with multivariable calculus, because everything is entirely separate and independent, every variable that is. So I guess we might as well dive into it. Okay, so as I said earlier, we are going over partial derivatives, and don't worry because they are incredibly simple. A partial derivative is essentially a derivative of a multivariable function where only the derivative of one variable is taken into account, and all other variables, despite their nature, are going to be considered constants. That is it. In fact, the most confusing thing about partial derivatives is the notation and the quote-unquote conventions. So first off, any function, and I'll get into the actual partial derivatives in a moment. Any function as a multivariable equation can be represented as f of whatever however many multivariable equations or multivariable variables exist. For the sake of this example, I'm just going to say x and y. So that is the way in which a multivariable equation can be represented. And this can be equal to anything. It can be equal to x plus y squared. And the derivative of this multivariable equation can be denoted as f sub x if we were to take it with respect to x, the derivative with respect to x. Whereas if we were to take the derivative with respect to y, we'd end up with f sub y. Now, as I said, when dealing with partial derivatives, you're going to take the derivative of one variable and almost entirely forget about the other and treat it as if it was a constant. So if we were to find the derivative with respect to x, I might as well just assign y squared to a constant a to make it easier. And so what we're doing is we're taking the derivative with respect to x of x plus a. Now, it isn't important in any way to notate your equation as this. I'm just doing this so you understand the idea behind treating some variables as constants. And of course, the derivative with respect to x of x is going to be equal to 1, and the derivative with respect to x of a is going to be 0. So this equation here, or the derivative of this equation with respect to x, is 1, because this over here is a constant. I'm going to do the same thing with y. So if we were to find the derivative with respect to x, we, of course, have to phrase it as such. And keep in mind, again, I cannot drive this home enough, that the variable not in consideration can be treated as a constant. So the derivative with respect to y of x is 0. And of course, the derivative with respect to y of y squared is 2y. So derivative with respect to x is 2y, derivative with respect to x is 1, at least in this instance. There is a separate way to notate multivariable equations. Understand that we oftentimes in Cartesian planes or univariable planes will represent an equation with y. And we can say that's equal to like 2x or something. In much the same way, a multivariable equation can be phrased as like c, or really any variable. A common one is z, although that's oftentimes treated as a variable as well. Let's just say a. Let's just say we have an equation a, and that's equal to, oh my God, hold on. And that's equal to e to the power of y plus x. The derivative with respect to y would be represented as dA dy. And that would be equal to e to the power of y. And of course, we don't add x because it's a constant. The derivative with respect to x would be 1 because this e to the power of y over here can be treated as a constant, as I've said. And what's great about these multivariable equations is that you can plug in values for variables as you typically would. So let's take a look back at this top equation over here, f of x and y. If I were to ask the question, what is the derivative of f with respect to y at 1, 2? All I would have to do is take this derivative, which as we already previously know is 2y, and then plug in our variable for y, which is 2. And so this over here is equal to 4. Keep in mind that the order in which the values for the variables are ordered corresponds to their placement over here as well. So x would be equal to 1 and y would be equal to 2. That's basically it for multivariable or partial derivatives, although I am going to dive in some practice problems. Okay, so this is the first question. We're given a multivariable function, f of x, y, and that's equal to 3x squared plus e to the power of x times y cubed. So we're told to find the derivative with respect to x. Off the bat, just to make it easier, I'm going to declare a as y squared. Again, this makes no difference. It's gonna make it easier to understand that this variable not in question is a constant. So f sub x, which is of course the derivative of xy with respect to x, is going to be equal to the derivative of our first term here. 3x squared, as you hopefully already know by the power rule, is 6x. And I would like to mention that all typical means of finding the derivative of something, like the quotient rule or the power rule, still apply in with partial derivatives. And so we got the easy term out of the way, and now is the next term. I'm going to rephrase this over here as e to the power of ax. Now, as you may or may not know, the derivative of, sorry, it's getting a bit cramped over here. The derivative of a function e to the power of ax is equal to the exponent, the derivative of the exponent times the original e to the power of ax. And so this over here would be equal to the derivative of ax times e to the power of ax. So we can rephrase that as e to the power of ax. And this applies because a, again, is a constant. And so f, oh, that does not look like an f now that I'm looking at it. Anyways, f sub x is equal to 6x plus x e to the power of ax. However, this is not in its most simplified form because, well, for one, we can factor out x, but we also need to plug in y cubed as a. So we can rephrase f sub x as x. Notice how I'm factoring it out. 6 plus e to the power of xy cubed. And that is practice problem 1, the derivative of fx with respect to x. Okay, this is essentially the same problem, except now we are finding the derivative of our multivariable function with respect to y. This shouldn't be too difficult. We are going to use the same practice we did earlier. I'm going to assign a as 3x squared. However, only one 3x squared appears, so I'm going to assign x to b. Because again, that is another instance of this over here, this x here is another instance of a variable we don't really care about because we're not deriving or we're not differentiating with respect to it. So I'm going to write f of y is equal to the derivative with respect to y of a, recall that we assigned 3x squared to a, and I'll get back to this in a moment, plus the derivative with respect to y of e to the power of by cubed. And as you know, the derivative of any the derivative of any constant is equal to 0. And so a over here is going to be equal to 0. I might as well write that over here. Notice how the derivative of 3x squared is equal to 0. That's because, again, it's a constant. And now we need to find the derivative of our second term, e to the power of by cubed. And as you would typically find the derivative of an exponential, you just take the derivative. You take the product of the derivative of the exponential times the actual function itself. So we are going to rewrite this as the derivative of the exponential, by cubed. So it's going to translate to 3by squared times e to the power of by3. That is the derivative of this term here. I'm going to transfer it over here. We still have a bit of simplifying to do because we need to plug in our variable y. I'm going to do that now. So f sub y is equal to 3by squared. As you know, b is x, so we can say this is equal to 3xy squared times e to the power of by cubed. Again, b is equal to x. And so this is how we take the derivative with respect to y of our function above here. And so that's practice problem 2. On to the final one. Okay, this is practice problem 3 and the final practice problem at that. We are given the multivariable function f, x, y, z, and that happens to be equal to cosine e times x plus natural log z to the power of x plus y. We want to find the derivative with respect to y at the points x equals 1, y equals 6, z equals 3. Notice how these values on these variables correspond. Okay, so those are supposed to be arrows, by the way. I know they look awful. So, as you know, f sub z denotes the derivative of f with respect to z. And recall that x and y in this instance, since they're not being taken into consideration, are going to be constants. So cosine e to the power of x, as you know, x in this instance is going to be a constant. So this is essentially saying cosine of a constant a, or cosine of 2, for instance. We don't know what these constants are. Nonetheless, the derivative of them is going to be equal to 0. So cosine e to the power of x is 0. This, on the other hand, is not 0, unfortunately, this next term. Natural log z of x plus y. Now I'm going to write the general formula for the derivative of, let's just say natural log a of x, a being a constant. This is going to be equal to the derivative of the argument, the derivative of a of x in this instance, which is going to be a, since, the derivative of x is going to be equal to 1, and that multiplied by a constant. Anyhow, the derivative of a times x is going to be a if a is a constant. The ratio of that and the argument itself, a of x, in this instance is going to be equal to 1 over x. I'm just telling you this such that we can find the derivative of the second term. So as I just said, the derivative of the inside over here, the argument, over the argument itself, I'm going to begin by writing the argument itself, z to the power of x plus y. And the numerator in this instance is going to be the derivative of this. So let's take the derivative with respect to z of zx plus y. Well, as we know, the derivative of y is equal to 0, so I might as well write that over here. However, the derivative with respect to z of z to the power of x is not that. Just to make this a bit easier, I'm going to assign, as I always do, one of our variables not in consideration to a constant, in this instance being c. So the derivative with respect to z to the power of c is going to be equal to z c times z to the power of c minus 1. Why is this? This is simply the power rule. Z in this instance represents the variable that's being taken with respect to, and c is just any constant. If I were to replace this with like, one moment. If I were to find the derivative of, let's say, just x cubed, it's going to be equal to the exponent times x to the power of 1 minus the exponent. Notice how that is exactly c times z to the power of c minus 1. It follows the same pattern because, as I just said, c is a constant and z is the variable in consideration. So naturally, they're going to follow the same pattern. And as I said earlier, typical conventions for finding the derivatives of functions still apply, such as the power rule. And so that's why z to the power of x with respect, the derivative of z to the power of x with respect to z is going to be equal to x times z to the power of x minus 1. And as I said, this is found in the numerator. So I'm going to add that over here. So that is f sub x, the derivative of our function with respect to z. I'm going to just omit the 0 because there's no point in a plus 0. That is not the end of our problem, however, as we need to find f of z at x equals 1, y equals 6, and z equals 3. To do so, we can just plug in our values into our derivative over here. So 1 in place of x is going to be 1 times z, which is 3, to the power of 1 minus 1, which is 0, over z, which is 3, to the power of x, which is 1, plus y, which is 6. And we can simplify this. Multiplying any value by 1 is pretty pointless. E to the power of 1 minus 1 is e to the power of 0, which is e to the power of 1. So I'm just going to write a 1 in the numerator. E to the power of 1 is 3 plus 6. We end up with 1 over 9. And so the value of this function here, the derivative of our function with respect to z at x equals 1, y equals 6, and z equals 3 is equal to 1/9, or 1 over 9, I should say. And that is it for this video over partial derivatives. I will continue publishing videos over multivariable calculus as I continue to learn them. However, if you do have any suggestions, I would appreciate it if you put them in the comments below. I will have a lot more time coming up, seeing as I'm on break now. All right, thank you.